Hello, students. I'm now going to just give a little voiceover narration to the PowerPoint that I had put into Canvas that was called Numerology versus Geometry on the abuse of mathematics in Plato's Timaeus compared to the judicious use of geometry in Galileo's Starry Messenger and dialogue concerning the two chief world systems. So you have read a portion of the Timaeus. In it, the main character doing most of the talking is this person, Timaeus. We don't know if there ever was an actual person named Timaeus. He only appears in two of Plato's dialogues, the Timaeus and another one named the Critias, and he plays the role of a Pythagorean, but we have no further evidence of him ever having existed. While we're on it, it's a possibility Pythagoras never existed. We have plenty of evidence about Pythagoreans, but we don't know for sure if there ever was a real Pythagoras. So the form elements must be composed of triangles. So that's one of the first points that Timaeus makes. He says, before the universe was organized, all things were in a state devoid of reason or measure. But then God began by first marking the four elements out into shapes by means of forms and numbers, and that God constructed them so far as he could to be as fair and good as possible. And so to a Pythagorean, to be as fair and good as possible is to be made out of triangles. In the first place, then, it is plain, I presume, to everyone that fire and earth and water and air are solid bodies, and the form of a body in every case possesses depth also. Further, it is absolutely necessary that depth should be bounded by a plane surface, and the rectilinear plane is composed of triangles. So if you've got a three-dimensional object, that thing has length and breadth and depth, and the sides then of this, let's say it's just a cube, are things that can be made of triangles. And then it turns out not just any old triangles, but two particular right triangles, the isosceles and the scalene. So the isosceles is the one that has a 90-degree angle, and then because it has two equal legs, that means the other two angles are equally 45 degrees. A scalene right triangle has a 90-degree angle, and the other two angles can be anything. And so he then talks about how everything can be made from these two triangles, and he describes them. And then he says, these we lay down as the principles of fire and all other bodies, proceeding according to a method in which the probable is combined with the necessary. But the principles which are still higher than these are known only to God and the man who is dear to God. So Plato is one of the most famous philosophers of all time, and he's especially known for two branches of philosophy, moral philosophy and epistemology. Epistemology, as you'll recall, is sort of the study of what we can know and how we know what we know. And he was a very astute epistemologist. So he is very aware when one of his characters is arguing from mere probabilities or from necessary conclusions. And so he says, we're going to combine the probable with the necessary in this explanation. Okay? Now, when we get to the scalene triangles, it's not just any old scalene, but the fairest. The right isosceles triangle possesses one single nature. So basically, every isosceles triangle is similar in that basically it has one 90-degree angle and two 45-degree angles. Now, scalene triangles have one 90-degree angles, and the other two can be anything under the sun. So he says there's one which is the fairest of all, and that is the one which, when you take an equilateral triangle, something that's 60, 60, 60, and all sides are equal, split it down the middle, and now what you have is a 30, 60, 90 scalene. And that's the one, he says, is the fairest of all scalene triangles. So then we have, we remember that Timaeus had already gotten Socrates to agree that since the material cosmos was merely a copy of an ideal cosmos, apprehensible by reason and thought. So again, things that you apprehend by your senses, they're kind of iffy. If they're apprehended by reason and thought, then you're getting at the real deal. So because of the fact that the physical cosmos is just a copy of the ideal cosmos, a merely probable explanation was good enough. He Timaeus then switches from probable claims, for example, which right scalene triangle was the fairest, to necessary claims about the 5 regular polyhedra. His explanations of the 5 regular polygons is real geometry. Okay, so then what he does is he proceeds to construct them. So he's telling you how each one is made. So you've got this tetrahedron. It's a simple regular polygon. So a regular polyhedra is made out of regular polygons. A regular polygon, all the sides are equal. So a triangle with 3 sides equal, a square with 4 sides equal, a pentagon that happens to have all 5 sides equal. You could have a pentagon that didn't have them all equal, but that would not make you one of the regular polyhedra. So what he does then is he goes through an explanation how each one of these things is constructed out of triangles. So the tetrahedron is made from 4 equilateral triangles. It's the smallest, simplest regular polygon, and it's sort of the pointiest one. An octahedron, you take 4 equilateral triangles and you make a pyramid, and then you put one on the top and a mirror image on the bottom. So now what you have is a regular polygon that is made out of 8 equilateral triangles. The icosahedron is made out of 20 of them. The cube is made out of 6 squares, but wait a second, he was saying that everything was made out of triangles. Well, you think of a square is made from 2, each square is made from 2 isosceles triangles, the ones that have a 90-degree angle and 2 equal sides. And so basically you take 12 isosceles triangles and it makes your cube out of the 6 squares. And then the dodecahedron has 12 regular pentagons. So those are the objects that Timaeus describes the construction of, and all that is totally legit geometry. As I said once before, these Greeks really knew a lot of geometry, and Plato was a very good geometer, so he knows his geometry. So when he's having Timaeus say this stuff, he's not just kind of blowing smoke. These are real necessary consequences. There are only 5 regular polyhedra, or convex polyhedra. There can't be any others. It can be proven that there can't be any others. So this then is that certain knowledge that he's talking about. So then Timaeus ends up with 5 polyhedra, but he only has 4 elements. Okay, so what he does is he assigns 4 of them to the 4 elements. The tetrahedron is the molecule of fire. The octahedron is the molecule of air. The icosahedron is the molecule of water. And the cube is the molecule of earth. He's got one left over, and he says God used it up for the universe in his decoration thereof. So in effect, these other things exist in the universe, and the universe would then be that dodecahedron. All right. He assigns the polyhedra to elements. And so this is where he has gone back into sort of pure probability. In the second paragraph, it says, wherefore we are preserving the probable account when we assign this figure to earth, meaning the cube, and the remaining figures, the least mobile to water, and the most mobile to fire, and the intermediate figure to air, and further, when we assign the smallest body to fire, and the greatest to water, and the intermediate to air, and again, the first in point of sharpness to fire, the second to air, and the third to water. As regards all these forms, that which has the fewest bases must necessarily be the most mobile, since it is in all ways the sharpest and most acute of all, and it must also be the lightest, since it is composed of the fewest identical parts, and the second comes second in point, and these same qualities in the third. So what he's done is he's taken properties of these regular polyhedra and attached them to the 4 elements. So the lightest and pointiest one is fire. The next one is air. The next one is water. The heaviest and sort of least mobile one is earth, and that's the cube. So then he has to address the fact, why can't we see the polyhedra in the elements? And he says, thus, in accordance with the right account and the probable. So when he talks about the right account, that is his mathematical necessary consequences. And the probable, that's when he's saying, it's like, okay, this one is probably the one that goes with fire and this one goes with air. When Thus, in accordance with the right account and the probable, that solid which was taken the form of a pyramid shall be the element and seed of fire, the second in order of generation we shall affirm to be air, and the third water. Now one must conceive all these to be so small that none of them, when taken singly, each in its several kinds, is seen by us. But when many are collected together, their masses are seen. So that's why when you look at a clod of earth, you don't see a bunch of cubes. When you look at some water, you don't see a whole collection of icosahedrons. That's because they're tiny. But when you put them together, what they do is they make the four elements. And moreover, as regards the numerical properties which govern their masses and motions and their other qualities, we must concede that God realized these everywhere with exactness, insofar as the nature of necessity submitted voluntarily or under persuasion, and thus ordered all in a harmonious proportion. So here is where he's relying on the fact that there are necessary relationships between and among these regular polygons and the polyhedra that you can make of them, and the fact that air acts like air and water acts like water and fire acts like fire and earth acts like earth. These are sort of the results of the perfection of God's composition of the elements out of these different materials. So then, connecting behaviors to shapes, having established probably which polyhedral compose which elements, Timaeus goes on to connect the behaviors of each element to the kinds of polyhedra or triangles that make them us. Thus, with a combination of probable and necessary, the geometry is accurate reasoning, Timaeus explains how God imposed order upon chaos by creating a universe in which the only four elements are composed of four regular polyhedra, while the fifth regular polyhedron, the dodecahedron, makes up the fifth element, the ether in Greek, or ether, the material that fills the universe in the region above the terrestrial sphere. Now, we'll compare this use of real geometry to support imagined material reality with the way Galileo uses geometry. Galileo uses real geometry to explain. While the geometry in the Timaeus explaining the composition of the regular polyhedra is fine, the use of geometry to explain the composition of the four elements is numerology, not mathematics. Two instances of geometry in the Starry Messenger are perfectly legitimate uses of geometrical principles to explain empirical observations. The geometry of telescopic magnification. After first giving his readers instruction on how to determine the magnification power of the telescope they had constructed, Galileo explains how, using geometry and a table of signs, they can determine the distance between objects as they appear to the eye of the viewer. So here then is that illustration, and what he says is, here's your instrument, and if you look over on the right side, you see the line FHIG. If you did not have a lens, then what would happen is the line FG would be coming to your eye through, just looking through a tube. But with the lens, what happens is the line HI fills up the entire optic. So that gives you an idea of sort of how much magnification is happening. And given that then these geometric relationships between things arriving in here, and you've got a table of signs, anything that you observe out there in space, such as a couple stars, you're going to be able to tell how far apart they are from each other. So then, even when wrong, he was right. Galileo's second explanation of why we don't see a jagged edge on the mountainous moon hypothesizes a lunar atmosphere, although no such exists. He needed to explain why, if we could see through such an atmosphere, it would obscure our perception of the jagged circumference of the moon. So if it's got an atmosphere, and it prevents us from seeing sort of a jaggy tooth edge around the circumference of the moon, why does it allow us to see the surface, which has dark spots and light spots and seems to have a lot of craters in it? The illustration below show that we would be looking through more atmosphere when viewing the circumference of the moon. So if indeed it had atmosphere, this diagram shows us by looking at the circumference, we're looking sort of diagonally through a greater amount of atmosphere. And that could explain why we could still see through one thin layer of atmosphere if we're looking directly at a crater at the moon, but we would be looking through a larger mass of atmosphere if you're looking at the edge of the moon. And then finally, Galileo correctly estimates the height of the mountains on the moon. Using current estimates of the diameter of the Earth, and that was pretty well known, and its relationship to the diameter of the Moon, that was pretty well known, Galileo estimates how high the mountains on the Moon must be to be casting the shadows of the size he observed with his telescopes. The diagram below illustrates the geometric argument on which he based his estimates, which were quite accurate. So he came up with very good accounts of how high those mountains on the Moon were. And then we get to the dialogue where we have these two characters, Salviati, who is speaking for Galileo, Simplicio, you might just call him Simpleton, is speaking for the Aristotelian Ptolemaic model. Early in the dialogue, Simplicio, arguing for the Aristotelian Ptolemaic system, attempts to support his argument by appealing to the authority of the Pythagoreans and the mystical perfection of the number 3. So he is using numerology, the person who represents the Ptolemaic Aristotelian view. Salviati, arguing for the Copernican system and representing Galileo's actual view, dismisses arguments from authority and instead resorts to geometric demonstrations with illustrations of why there can only be 3 spatial dimensions. So, Plato knows his geometry and uses it to good effect to explain how the 5 regular polygons are related. But then his connection of those polygons to the 4 elements, and then the 5th one to the quintessence, the 5th element, is just mumbo jumbo. Galileo knows his geometry, and in these cases where he is putting in illustrations into his document, he's making very good use of the necessity, the necessary consequences of geometric relationships between items. So I hope all of that is clear. If not, you're going to have an opportunity to ask about it next class meeting. Talk to you later.